Today we're doing question 13 from the 2023 AMC 10B, and the question is, a rectangular box P has distinct edge lengths A, B, and C. Note that they're distinct. The sum of the lengths of all 12 edges of P, is 13. The area of all 6 faces is 11 over 2, and the volume is 1/2. What is the length of the longest interior diagonal connecting the two vertices of P? First of all, if we look at the first one, there are four of the same lengths at once. Like if you look at a cube, in this case, a rectangular prism, there are 4 of each length. So, the first one is saying 4a plus b plus c equals 13. And then, from the second one, the area of all 6 faces is 11 over 2. So, there are 2 identical versions of each face. They don't look very identical in my figure. They are, in fact, identical. And they are the second symmetrical sum of A, B, and C here. So, and there are 2 of each. So 2AB plus BC plus CA equals 11 over 2. And next up, the volume is 1/2. So that is quite simply ABC equals 1/2. Okay, now that we've reached this point, what do ABC, AB plus BC plus CA, and A plus B plus C look like? If you thought what I was thinking, and that I was hinting at, they are symmetric sums. Symmetric sums. So if you've ever seen these anywhere, they are probably with the higher degrees of Vietas. So immediately, let's jump to Vietas. So what we are going to do next is we will make a 3rd degree polynomial that has roots A, B, and C. Because we know A plus B plus C, AB plus BC plus CA, and ABC, we know some ratios of the coefficients, and therefore, once we get the polynomial, we can then solve the polynomial, get A, B, and C, and calculate the final answer. So, let's get to it. So, we can first remove the coefficients there. So A plus B plus C equals 13 over 4. And if you remember Vietas, that is negative B over A. And then AB plus BC plus CA equals 11 over 4, which is C over A with Vietas. And ABC is 1/2. In other words, is negative D over A with Vietas. So, we can continue using these, switch to black, and we can find the polynomial. So looking at the fact that 2 of these have 4 as a denominator, let's set A equals 4. So very clearly then, B is negative 13. And then just by looking, C is 11, and D is, well, this is also equal to 2 over 4, so D is negative 2. And then let's construct the polynomial. If you don't remember, a 3rd degree polynomial is in the form ax cubed plus bx squared plus cx plus d. This is what Vietas is referencing. So it becomes 4x cubed minus 13x squared plus 11x minus 2. And now we must find the solutions to this polynomial. We must find the roots of this polynomial. A very simple trick that helps you solve cubics and higher degree polynomials is add the coefficients. If they add to 0, then you can divide the polynomial by x minus 1 and get a very nice quadratic that you hopefully know how to factor. So if you add these up, 4, negative 9, 2, 0, it works. We divide it by x minus 1, And we get 4x squared minus 9x plus 2, I believe. And then from here, we factor this butterfly away. I got the numbers way messed up there. They are these. Calculated them earlier, forgot them, sorry. So now we finish the factorization. And we can find the roots. They are 1, 1/4, and 2. So knowing these roots, we remember the formula and what they're looking for. Do not add the roots. That is a common error here. What is the length of the longest interior diagonal? So if you remember what that area is, that length is, that is just the square root of a squared plus b squared plus c squared, where there a, b, and c are the side lengths of the cube. In this case, the roots for x, the polynomial. So we can plug in and get something like 1 plus 1 over 16 plus 4, or 81 over 16, or 9 over 4. That is our answer. And if we go back up to the question, that's choice D.